Hello and welcome to this homework help video where I'm going to go over two homework problems, one involving a girl and a pulley and the other a pair of fish. So let's go ahead and take a look at this first one, which is all about the idea of a machine which is getting mechanical advantage. All right, and let's go ahead and write that down. So we have that machines give mechanical advantage. Those are some key terms for you. And what mechanical advantage means, what that particular jargon term means, is it means that it is a force multiplier. So it has a certain amount of input force that is going to be less than the output force. Okay? So the key idea here is that we have a relationship where we have F out greater than F in. A famous example of this is a lever with a particularly located fulcrum. So we'll put our fulcrum, which is just the pivot point, think a teeter-totter, but not a teeter-totter that's the same length on both sides. And if we had a lever that looked something like this, so that this length on the short end was L, and the length on the long end was, say, 5L, then you would have a output force that was five times larger than the input force. But you would also be giving up distance because energy has to be conserved. The conservation of energy is never invalidated, and this is no exception. So the energy in has to equal the energy out, despite the increase in force. So energy in equals energy out. Now, by the definition of work, that tells us that work is just force multiplied by distance, and we know that work itself is easily equated to energy. In fact, it is just a form of energy in transition. We know that we can just write this equation as force in times distance in equals force out times distance out. So I didn't call attention to this as being our sort of key equation, but in a way it really is. There is a harder time with this particular problem pinning down one key equation because there are so many ways to go about it. So instead of calling it a key equation, I'll go ahead and put a box around it, okay, as a good potential equation to use and one of the key ideas. So let's now actually take a look and solve part A, but I'm going to mix up the values a little bit. So let's go ahead and change our numbers. And you may see different numbers as well if you're doing this problem yourself. So let's go ahead and make the distance that the girl steadily pulls the rope up. We're going to make that, let's make it 1.2 meters. And we're going to go ahead and have her pull with a steady force of 111 newtons. Okay. And also I want to get my calculator open as well. All right. So let's go ahead and have Desmos open. And we'll readjust the screen there. Okay. So with all that in mind, let's go ahead and take a look at how we're going to answer part A. So we are asked by how much does the potential energy of the block increase with the values that I've chosen of the girl lifting 1.2 meters with a constant steady force of 111 newtons. Okay? Well, what we have here, right, is we have that the work that she does has to be force times distance. Okay? So we know by definition that work, always represented by a W, is force times distance. Notice I'm not putting a subscript of in or out because this is a general idea. It always applies, okay? So that means that the work that she does has to be the same as the work that is done on the block because energy can't just be destroyed, it can't disappear, and it can't just come out of nowhere either. So there has to be a conservation of energy. And that matters because we're asked about the potential energy of the block. How much does it gain in potential? Well, things gain potential energy when they're lifted up. And we can see here that indeed the block is going to be lifted up. And it's going to be lifted up a particular distance. Now, it's not going to be the same as the distance that she lifted up, which we'll come back to in part B, but the energy will be the same. So let me kind of show what I mean by actually plugging in some values here. So I'll have the work done by the girl is just going to be her steady force of 111 newtons multiplied by the total length of rope that she pulls through her hands of 1.2 meters. All right, so that's going to be 111 times 1.2. Okay, so that is 133.2. What are the units on that? Joules. Okay, so you can also sometimes see it as Newton meters, but here we're calling this joules, which is the standard unit of energy. Okay, in the metric system. What are we going to do with that 133.2 joules? Well, it turns out that's our answer, because whatever work the girl does has to be equal to the change in potential energy of the block. Yeah, I can remember if it's a block or a box, but it's a block. Okay, so there has to be an equation there. Why? Because of conservation of energy. Okay, because energy, remember, work is just a form of energy. Energy is conserved. And there's nowhere else that her energy can go. We're not told about any friction. There's nothing else that's being lifted. The rope is of negligible mass. So in a simplified system like this, there's nowhere else for her energy to go. It has to go to the block. And the block, right? It's not picking up speed. It didn't gain kinetic energy. It only gained potential energy. Now, could that be made explicitly clear by, clarifying some of those ideas and saying that it doesn't gain kinetic and so on? Yes, but when you solve a word problem, you also want to keep in mind that the problem is solvable as written. And if there was, say, friction or heat, or these other being other forms of energy, or the block picking up speed and thus having kinetic energy at the end of the lift, well, in those cases, you'd have to be given extra information, which you're not. Okay? So then we know that our answer is none other than the 133, if I round, joules of potential energy that the block gains. Now we're asked to find the mass. So how do we go about doing that? Well, to do that, let's now write down the form of potential energy. So potential energy has a couple of forms. There's one form for springs, for example. There's also potential energy in electrical systems. But the most common type of potential energy is gravitational potential energy, which I've put a little g here to denote that we're talking about gravitational, right? G for gravitational. And the fact that the lowercase g is not, by chance. It's because we're talking about gravitational potential energy on the surface of Earth, where gravitational acceleration is g, as in g-force, as in 9.8 meters per second squared, or approximately 10 meters per second squared. And we'll stick with the approximation, so we'll round to 10. And in equation form, that potential energy is m for mass, g for the aforementioned acceleration, the 10 meters per second squared, okay, gravitational acceleration on the surface of Earth, our home planet, and then h, okay, which is just the height, the distance that you gain in the vertical direction. So if you lift something up, it gains potential energy. If you lower something down, it loses potential energy. Okay, now, we know that this gain in potential energy is none other than the value that we had in part A. So all we have to do then is solve for m. However, there's a caveat, because you might then say, oh, now I'm going to use the value of h, the 1.2 meters. But you can't. That would be incorrect. You'd get exactly half the correct answer, because you can't use h, you have to use half of h. Okay? Now, why is that? Well, because of energy conservation. Because think about the fact that this is a machine. This is a pulley, okay, which essentially is a rounded lever. And that means that there is a doubling of force. Because if we think about the force that the girl is doing, because let's go ahead and have a pink arrow here to denote the force. So she's pulling with a certain amount of force. We would call this a tension force, but that's not the only tension acting on the block, is it? Right? Via the pulley. There's also a tension force on the other side. So that's the beauty of pulleys. That's why people use them, because the force that you put in is precisely doubled. Okay, because they're two equal tension forces. We know they're equal because there's nothing else to support them. They're both supporting the same thing collectively, and they both have the same angle. They both point straight up. If one of the ropes was angled, then that would change the equation slightly. But here, they're both pointing straight up, so they equally share the burden, which means they are equal value tension forces. Okay? Now, we know her force is 111, right? That means that the force acting on the block would be 222, right? Or conversely, we can say, well, if we have a conservation of energy, then we have the work that she did, right? So the work done by the girl equals the work done on the block, okay? Now, you might be like, well, we already know that. It's just, it's the value we got. It's the 133 joules. But if we write this slightly differently, and we write then the force of the girl, distance, right? That's the rope that actually goes through her hands, right? The distance she pulls. And then that would equal the force of the block, okay, times the distance of the block. Well, there you see it, right? Because since the force experienced by the block is exactly twice as big as the force experienced, or the force that the girl exerts, that 111, the block must go half as far. Okay, so we have that D block equals 1/2 D girl. All right, and that's simply because F block is going to be 2F girl. All right, and if you want to kind of write that out yourself and make sure that you can see where that 2 comes from and how it becomes a 1/2 when you divide both sides by it, then you'll have that further practice yourself. 2 times F girl, like so. Okay, so this would be this is the idea that I was explaining. All right, and this is the consequence of that idea. All right, so now if we go back to potential energy, and again, we could have come at this differently, hence the the hesitation of myself to not say, oh, this is the key equation, because it's a little bit less direct like that. Then we go over here, and now we're going to write mg. Okay, now h, that's the distance that the block goes up, which now we know is 1/2 d. I left off the girl, but that's just 1/2 d. Okay, so that d is none other than the 1.2 meters. So half of that is 0.6 meters. Okay, so now you see that we are ready to solve this because we know the energy is conserved, so we know the left-hand side is 133 joules. We don't know m, that's what we're going to find. We know that g is 10 meters per second squared, and then we know that 1/2 d is 0.6 meters. Okay, all right. Didn't work. Oh well. So then we're going to go ahead and by what I was talking about didn't work is trying to move the text. But let's go ahead and forget that and move on to find the value of m, which is simply going to be taking the 133, and that was unintentional there, the 133 joules, and dividing by 10 times 0.6, which would just become 60, right? And that would be 60 meters squared per second squared. Okay, which will give us units of kilograms because a joule is a kilogram meter squared per second squared. So a joule divided by a meter squared per second squared just leaves the kilograms behind. And so we're just going to get 133 divided by 60. Okay, so let's go ahead. I'm going to round here, which I normally wouldn't recommend, but since we're already rounding gravity, it's not that big of a deal. And we'll just go ahead and divide by 60. And then we get that the mass must be 2.22 kilograms. All right, well, there you have it. There is your approach to solve that first problem. And you can see I still unintentionally moved our background. Let's see if I can get it lined up more or less. Nope. Try that one more time. All right, close enough. Okay. All right, so there we have it. And let's put this one in red to be consistent and so that it's actually in place again. So 2.22 kilograms. All right, so now let's carry on to the second problem. And please excuse that some of the wording here is underneath my writing. Again, because I accidentally moved the figure or moved the background. Okay, so in the second problem, we're not going to be dealing with energy conservation, but we're still going to be dealing with a conservation, which makes sense probably talk about these two problems together. So in this problem with these two fish that are colliding, yes, one's eating the other, but essentially it's a head-on collision. It could be cars or raindrops or billiard balls or anything, just two things smashing together. Well, they're going to smash together and they're going to stick together. That's called an inelastic collision. So any collision that involves two objects coming together and sticking is an inelastic collision. Okay, so this is an inelastic collision. The opposite of that, by the way, if opposite is the right word, is an elastic collision, where two things crash together and then bounce off with no loss in energy. An inelastic collision has a loss of, I shouldn't say a loss of energy, but a loss of mechanical or kinetic energy, because that energy has to be converted to something else for the things to stick together. Maybe it's being converted to, some other form of mechanical energy like Velcro, right? But at a smaller scale. Maybe it's getting converted to heat energy when two things stick together, right? Maybe it's getting converted to some sort of electromagnetic energy to allow things to stick together like magnets, but you can't have things stick without energy. And so when you have an inelastic collision, you lose the mechanical energy, which is to say the kinetic energy of the motion, and it gets converted over to something else. Now, what's great about inelastic collisions is they are the simplest to deal with, and they're the only ones that you will have to solve in a class like this, okay? So what is our information? Well, now, in a problem like this, we'll be usually given the mass of both fish, and then maybe ask for what are the missing velocities, such as what are the two initial velocities of the fish, or maybe you're asked to solve for what are the mass of the fish, and you know both of the velocities. So let's take a look what we know here. So we have a fish, which I'm going to change its mass to, let's make it a 5.2 kilograms, a big fish. How about we have a little bit smaller, 4.4 kilogram fish that's swimming at a speed, well, yeah, that's fast speed. I'm sure barracudas swim that fast, but let's have 0.9 meters per second as its velocity, its swimming speed, okay? And then we're going to have our other fish that's about to be swallowed, our absent-minded one, which is the lighter, smaller fish. So it makes sense that our big one here is the one with the, I chose 4.4, okay? And then the smaller one in the original problem, in the original values, was 0.5 kilograms. Let's go ahead and make this one even smaller. We'll make it 0.21 kilograms. Okay, and so there are our relevant values. You see we have 3 of them. Now, what's great about this problem, it is very much a problem where we can say, here is the one key equation. So let's go ahead and write that down. So our one key equation for this problem is this right here, which says that we have V1 M1 plus V2 M2. Put a dot on both of those to show multiplication. Okay, so this is just V denoted as 1, M denoted as 1, V denoted as 2, and M denoted as 2. Those are subscripts, obviously, and what that means is it's just the velocity of object 1, the mass of object 1, plus the velocity of object 2 and the mass of object 2. In both cases, it's the product of the velocity and mass. The product of velocity and mass, do you remember what that's called? That's called momentum. Okay, that is the definition of momentum, velocity multiplied by mass. Okay, now to finish off our equation, what's on the other side? Well, it's just the total mass, so M1 plus M2, because our two objects are going to stick together, in this case, the two fish, and then some final velocity. Okay? All right. So let's go ahead and take a look here. So we have swimming at one minute swallows opposite-minded fish, swimming in the, swimming towards it at a velocity that brings both fish to a halt. Okay, so we're given one other piece of information, and just like a good word problem, we are given it in words rather than values. Because a lot of times, all your information is given to you in values, but not all the time. Sometimes you're told something like an object begins at rest or an object finishes at rest. And indeed, that's exactly what happens here. Our new combined object, the one fish having swallowed the other, okay? So this object now that has a total mass of M1 plus M2, well, that is going to be at rest after the collision. So what does that tell us? That tells us that V final, okay? Put over here in green so you separate it from the information in the problem above. So V final is 0 because that's what it means. It finishes at rest. Okay. So I think we're all good to actually plug things in now. So we're going to take our 3 known values and find our 1 missing value. Because what we don't know is how fast the absent-minded lighter fish was swimming before it got swallowed. And I'm actually going to add a little bit of detail here to the figure and show the values clearly on the picture. So this is what I called V1 for the big one. So this would be M1 for the big fish. Okay, so that's its initial velocity and its mass. Mass never changes, but it gets combined with the other one. And then we have the mass of the other fish, the light fish, M2. And then the unknown value is then going to be V2. And then afterwards, there's just going to be the orange fish. You won't be able to see the light purple fish because this will be inside the orange fish. And that's where we have V final equals 0. Okay, so let's go ahead and plug in all of our values and see how we would go about doing the algebra and solving this. Okay, so for V1, we have, it's over here, 0.9 meters per second. So 0.9 meters per second times 4.4 kilograms. So that's it for the big fish. Okay, now, for the small fish, should I have some negatives on it? Absolutely, because the small fish is moving in the opposite direction. So a good way to be clear about where to have your negatives and where not to is to say, to yourself, right? So self, I'm going to call the positive direction this way. I'll call it positive x because it kind of makes sense to call horizontal things x. And that means that the big fish is moving in the positive direction, so its v is positive, and the small fish, the one that gets swallowed, must be moving in the negative direction. So it's got to have a negative velocity. So that's going to show up right here, because then we're going to have plus some negative velocity. We know it has to be negative. That way, when I solve for it, I'm going to be solving for the value, just this numerical value, having already taken into account its direction. And then here I'll put the 0.21. On the other side, I'm going to have the sum of masses, so 4.4 plus 0.21. And let's see what that is. That's going to be 4.61. Okay, so that's m1 plus m2. And then our known final velocity, which is a 0, which actually means I could have skipped the whole step of finding m1 plus m2, because anything multiplied by 0 is just 0. Okay, so then we'll go ahead and want to solve for v2. Since this product here is negative, if we add it to both sides, it'll become positive when we add it to the right. And if we add it to the left, then it'll cancel itself out. And so all I mean by that is that I'm just going to take, all right, let's take a thinner pen here. We'll take plus v2 m2, right? Remember, m2 is the 0.21 kilograms, which I left off the units, which I don't like to do. And then I'm going to add that to both sides, see? And that means that this one cancels out because, adding the positive version of something to the negative, right? It's like taking -5 and adding +5, it just becomes 0. So then we're all ready to actually solve for this. And we're going to have on the left-hand side, we'll just have that product of 0.9 and 4.4, which I'll go ahead and calculate now as an intermediate step. So 0.9 times 4.4 is going to give us 3.96. The units would be kilogram meters per second, sometimes also called Newton seconds, but there's no special letter that's used for momentum. So kilogram meter per second is fine. And then over on the right-hand side, we'll have the value that we're solving for algebraically, V2, and then our known mass of 0.21 kilograms. So now, of course, we divide both sides by the 0.21 kilograms, like so, and that's going to be our answer, and we'll be done. Okay? So then I'll go ahead and then, kind of do the mirror image of the equation, because you can always do that, just so that I'm reading from left to right, and I got my V2 over there, and all I want is this 2, because of course this side now is all cleaned up. There's nothing left except the V2. So then the V2 is just going to be equal to the initial velocity of the small fish is just going to be 3.96 kilogram meters per second divided by 0.21 kilograms. And of course the kilograms will cancel. And so we're going to be left with meters per second, which makes sense for a velocity. All right. So let's see what we get. We're just going to take that 3.96 and we'll go ahead and divide by 0.21. So we find that the small fish must have had a velocity of 18.9, so really fast, which makes sense for it to bring the bigger fish to a halt. So it was really moving fast. I'm not sure how it was moving that fast. It's like 70 miles an hour or something, but it goes right into the mouth and it gets swallowed. And then that big fish is bumped right to a stop. And that's our answer. So that would go right up here, 18.9 meters per second. So there you go. That concludes this homework help video. I hope it has been helpful. Thank you so much for watching.